All right, let's jump right in. For this explainer, I'm putting on my chief engineer's hard hat, and I'm asking you to put on your CFO hats, because we need to evaluate a surprisingly critical piece of your infrastructure: piping systems. Now, I know for a lot of executive stakeholders, there's this really dangerous temptation to treat piping as just another commodity, right? Just a line item on a spreadsheet that you want to minimize. But as we're going to see today, treating your process lines as basic commodities is a massive financial risk. So consider this a critical engineering and financial briefing to completely reframe how you look at material specification.
Okay, let's dive right into this with a quick cautionary tale. We had a procurement manager at a food processing plant who decided to swap their piping spec from grade 316L stainless steel down to a cheaper 304 grade. His grand plan? Cut initial capital costs by 12%. And hey, it looked fantastic on the spreadsheets. But the pipes? Well, they didn't read the spreadsheets. 6 months later, chloride-induced pitting completely chewed through 3 sections of their transfer line. The resulting unplanned shutdown and emergency fixes ended up costing 4 times the amount he originally saved. It's a harsh reality, but choosing the right material isn't just some minor engineering detail, it's literally the difference between a reliable 20-year asset and a catastrophic recurring liability.
So, here's our roadmap for this explainer. First, we're going to tackle the CapEx illusion and really secure the financial argument for advanced materials. Then, we'll contrast 2 wildly different environments: the microscopic purity you need in sanitary food processing and the sheer macroscopic brutality of high-pressure oil and gas. And finally, we'll outline a strategic lifecycle optimization framework that you can apply to any major capital project.
All right, Section 1, the CapEx illusion and total cost of ownership.
When boards judge piping investments strictly by the upfront price tag, they're buying into a profound illusion of savings. Just take a look at this simplified 50-year projection for a 1-kilometer section of a district heating network. Look at that initial capital row. Sure, the pre-insulated stainless steel system has a 50% premium upfront. It's 750,000 euros compared to just 500,000 for the carbon steel. But fast forward to year 26, the carbon steel pipe corrodes, fails, and demands a massive inflation-adjusted 1.5 million euro replacement. The stainless steel system, 0 replacement costs. Plus, when you factor in the cumulative energy loss from poor insulation and the high maintenance costs of constantly patching leaks, that carbon steel system is just bleeding money every single year.
The math here is undeniable. Over a 50-year life cycle, the total cost of ownership for the premium stainless steel system is actually less than 1/3 of the quote-unquote cheap alternative. The big takeaway for us is that investing in the correct, higher-grade material on day one isn't an expense. It's a highly effective financial strategy to wipe out future liabilities.
Moving on to Section 2, Sanitary Food Processing Systems and Microscopic Purity.
If you're in the food and beverage industry, whether that's dairy, brewing, or pharma, compliance with strict sanitary standards, like 3A or ASME BPE, is absolutely non-negotiable. And it all comes down to the internal finish of the pipe. Standard industrial pipes might look nice and shiny on the outside, but inside, they're a microscopic mountain range of weld seams and rough walls. For food processing, you need sanitary tubing mechanically polished to an incredibly precise roughness average, or RA. We're talking about an RA of 0.8 micrometers or less. To put that into perspective, a typical bacterium is about 1 micrometer wide. So a single microscopic scratch can harbor that bacteria, let it survive automated clean-in-place cycles, and trigger a massive, brand-destroying product recall.
But even within those sanitary systems, you have to be highly strategic about your alloy. Grade 304 stainless steel is your trusty, cost-effective standard for general dairy, beer lines, and stuff with low chloride exposure. However, if you're processing high-salt foods, think sauces or pickles, or if your cleaning systems use aggressive high-temperature acids, grade 316L becomes mandatory. Why? Because 316L contains an added element called molybdenum, which acts like an invisible shield against chloride-induced pitting. If you skimp and use 304 where 316L is needed, you will inevitably experience the exact kind of catastrophic failure we talked about in our opening story.
All right, Section 3, High-Pressure Oil and Gas, or as I like to call it, macroscopic brutality.
Now we are pivoting completely from microscopic purity to macroscopic pressure. Offshore platforms and petrochemical refineries face just unbelievably severe environmental hazards every single day. We're dealing with highly toxic hydrogen sulfide in sour gas, incredible levels of corrosive chlorides from seawater, crushing subsea pressures in deepwater drilling, and extreme thermal cycling that can shoot past 1,000 degrees Fahrenheit. In environments like this, traditional carbon steels aren't just inefficient, they're actively under siege.
Now, what's really interesting about this is how the metallurgy evolves to meet those threats. Enter the duplex families. These alloys combine austenitic and ferritic crystal structures to give you massive mechanical strength and corrosion resistance. Duplex 2205 is fantastic for intermediate pressures, offering excellent resistance to stress corrosion cracking. But for the absolute harshest, most punishing subsea environments, engineers deploy Super Duplex 2507. It boasts a pitting resistance equivalent number, or PREN, of over 40 that effectively guarantees decades of immunity to severe localized corrosion, keeping you safe from disastrous environmental leaks and crippling downtime.
Which brings us to Section 4, Lifecycle Optimization Strategy through Zone-Based Material Selection.
So how do we actually build this into an actionable plan for the executive team? Well, you definitely don't need to build an entire facility out of the most expensive material. That totally kills your CapEx. Instead, you use a targeted 3-step engineering discipline: zone-based material selection. Step 1. Meticulously map the specific process conditions, the temperature, pressure, chemicals, zone by zone. Step 2. Deploy your high-cost materials like Super Duplex strictly in the most aggressive high-risk zones, like a high-pressure brine line in a desalination plant. And Step 3. Optimize your budget by utilizing standard grades like 316L for low-intensity areas like raw water intakes. In one documented project, doing exactly this saved nearly 15% in upfront piping costs while completely securing the plant's long-term reliability.
This strategic approach ensures that your capital is deployed exactly where it provides the maximum long-term value. We are moving way beyond that simplistic good, better, best procurement mentality and adopting a highly sophisticated, data-driven framework for modern plant design.
Which brings me to the final thought I want to leave you with in this explainer. When you sit down to evaluate your next big infrastructure project, you have to ask your team, are we just buying pipe or are we investing in 50 years of operational certainty? Shifting from a short-term commodity mindset to a long-term, value-based investment strategy is honestly the only way to secure your infrastructure, protect your brand, and maximize your profitability. Thanks for joining me, and I really hope this framework helps make your next engineering investment your best one yet.